Good morning. In the previous section, we have discussed about various topics of design of transformers. So, in the last, we have discussed about the main dimensions of the transformer and one numerical we have seen regarding the design of core. In today's lecture, I am going to discuss about two main points. One is design of transformer tank and the voltage regulation of a transformer, and also we'll solve one example on design of transformer tank. So here I am going to share some of the files which will give an information about today's topics. So in this case, first we'll see the design of tank with the tubes. Now the tank is also a part of the transformer. In case of the transformer, because of the losses in the core and coil, the temperature of the transformer increases. Because of the losses in the transformer core and coil, the temperature of the core and coil increases. In small capacity transformers, the surrounding air will cool the transformer effectively and keeps the temperature rise well within the permissible limits. As the capacity of transformer increases, as the rating of the transformer increases, as the size of the transformer increases, the loss and the temperature rise increases. In order to keep the temperature rise within the limits, air may have to be blown over the transformer. This is not advisable as the atmospheric air containing moisture, oil particles, etc. may affect the insulation. To overcome the problem of atmospheric hazards, the transformer is placed in a steel tank filled with oil. The oil conducts the heat from core and coil to the tank walls. From the tank wall, the heat goes dissipated to the surrounding atmosphere due to the radiation and convection. Further, as the capacity of transformer increases, the increased losses demands a higher dissipating area of the tank or a bigger sized tank. Please remember, as the capacity of transformer increases, the increased losses demands a higher dissipating area of the tank or a bigger sized tank. This calls for more space, more volume of oil, and increases the cost and transportation problems. To overcome these difficulties, the dissipating area is to be increased by artificial means without increasing the size of the tank. By artificial means, we need to increase the dissipating area and the size of the tank. The dissipating area can be increased by what? By these four particular methods. One is fitting fins to the tank wall. Second, fitting tubes to the tank. Third, using corrugated tank. Fourth, using auxiliary radiator tanks. Since the fins are not effective in dissipating heat and corrugated tank involves an constructional difficulty, they are not much used nowadays. The tank with tubes are much used in practice. Whatever the tanks are there with the tubes, they are used much in practice. So now, going further, heat goes dissipated to the atmosphere from tank by radiation and convection. It has been found by experiment that 6 watt goes radiated per meter square of plane surface per degree centigrade, and 6.5 watt goes dissipated by convection per meter square of plane surface per degree centigrade. Please remember, it has been found that 6 watt of the power radiated per meter square of plane surface per degree centigrade, and 6.5 watt goes dissipated by convection meter square of plane surface per degree centigrade. So thus total how much? 12.5 watt per meter square degree centigrade goes dissipated to the surrounding. Dissipated to the surrounding. So if theta is the temperature rise, then at final steady temperature condition, losses responsible for temperature rise is losses dissipated or transformed losses. This is given by 12.5 st theta. 12.5 st theta. So losses dissipated or transformed losses will be 12.5 st theta. In this case, whatever the st is there, heat dissipating surface of tank, heat dissipating surface of tank, and theta is given by total loss divided by specific heat dissipation into surface. So Pi plus Pc divided by 12.5 st. So now number and dimensions of the tubes. In order to have the number and dimensions of the tube, we will have to consider that if the temperature rise of tank wall is beyond a permissible value, let us say 50 degrees centigrade, the temperature rise of tank is more than this, then cooling tubes are to be added. Cooling tubes are to be added to reduce the temperature rise. With the tubes connected to the tank, dissipation due to radiation from a part of tank surface screened by the tube is zero. So there is no change in surface as far as dissipation of heat due to radiation is concerned, because the oil when get heated up moves up and cold oils down. Circulation of oil in the tubes will be more. Obviously, this oil circulation increases. The heat dissipation and convection from the tube increased by 35%. Now, let us go for the number of tubes. Calculation of number of tubes. So in order to have this number of tube calculation, we need to consider this first. This is already stated. Dissipating surface of tank ST is, that is ST. Then it will dissipate how much power per degree Celsius. This is 12.5 ST watt per degree Celsius. Let the area of tube is x into ST. Area of the tube is loss dissipated by the tube by convection. It is 35% we had seen. It is 1.35 into 6.5 into xst. It is 8.8 xst. Total loss dissipated by the tank and tube. Total loss dissipated will be this. The loss dissipation is 12.5 STW per degree Celsius plus this 8.8 loss dissipated by the tube by convection. 8.8 into xst, it is overall this. Now total area of tank wall and tubes st plus xst. Now loss dissipated will be this thing. Now theta, we know that Pi plus Pc divided by st, 12.5 plus 8.8x. Now x will be given by just here by this equation. You can write x as this thing. Now going further, the total area of the tubes is 1 divided by 8.8 under square bracket Pi plus Pc divided by theta minus 12.5 st. Please consider this. LT and DT be the length and diameter of these two. Now area of each tube will be pi dt LT. This will be very helpful in solving the example. Please remember, the area of each tube is pi into dt LT. pi into dTLT. Now the number of tubes NT will be 1 by 8.8 phi dTLT pi plus PC divided by theta minus 12.5 ST. Now this is the equation for NT, number of tubes. Now here what we need to consider is the diameter of tubes are normally 50 mm and they are spaced at 75 mm. Please remember, if say there are two tubes, so the diameter of tubes will be 50 mm and they are spaced at 75 mm. Whatever the distance between the two tubes is 75 mm. So now we'll see the cooling of this transformer. So in this case, the cooling of the transformer, there are various type of cooling methods. So these are air natural forced circulation of oil, air blast, oil forced air natural, oil forced air forced, oil natural air forced, oil forced water forced, oil natural water forced. These are the various methods of cooling of transformer. This choice of cooling method mainly depends on the size, type of application and type of conditions obtaining at the site where the transformer is installed. And this is about the different type of cooling methods. So now if you see the main dimensions of this particular tank, here, yes, this is the main dimensions of the tank. So in this case, what we need to consider is, so in the main dimensions of the tank, the dimensions of the tanks are decided by the dimensions of the transformer frame and the clearance required on all sides. Whatever the dimensions of the tanks are there, they are decided by the dimensions of the transformer frame and the clearance required on all sides. So in this case, we are going to see these dimensions first: C1, C2, C3, C4. So this C1 is nothing but the clearance between the winding and tank along widthwise. C1 is given by clearance between the winding and the tank along widthwise. Now this C2 is given by clearance between winding and tank along lengthwise. This is clearance between the winding and the tank along lengthwise. This is widthwise, this C1, and this C2 is lengthwise. Now C3, this C3 is there. It is the clearance between the transformer frame and the tank at bottom. This is clearance between the transformer frame and tank at bottom. Now one more is remaining, that is C4 is remaining. This C4 is clearance between the transformer frame and tank at bottom. Clearance between the transformer frame and tank at bottom, C3 and C4. So now if you see the total height, total length, total width of the transformer tank. So here that is the total, we can see. Now This is the tank height HT. It is HW plus 2HY or 2A plus clearance 32 60 centimeter for single and three-phase core single phase cell type transformer. And it is total length of the tank, and this is total width of the tank. Total width of the tank. So this is about the dimensions of the tank. Now we will solve one example on the design of transformer tank. So let us see this example. This example you can see. Design a suitable cooling tank with cooling tubes for a 500 kVA 6600 bar 440 volt 50 Hz 3-phase transformer with the following data. Dimensions of the transformer are 100 centimeter height, 96 centimeter length, 47 centimeter breadth. Total loss is equal to 7 kilowatt. Allowable temperature rise for tank wall is 35 degrees Celsius. Tubes of 5 centimeter diameter are to be used. Determine the number of tubes required and their possible arrangement. This is the question asked. In this case, in order to have the number of tubes required, that is NT. This is the formula for number of tubes required, NT. And this is the arrangement, you can see how the arrangement. Yes. So in order to calculate number of tubes, what we require is AT divided by AT. Capital AT, it is area of all the tubes, divided by small at, that is dissipating area of each tube. Dissipating area of each tube. Dissipating area of each tube, AT is pi into diameter of the tube, average height or length of the tube, then area of all the tubes, AT, we need to calculate it. So let us have tank height as HT first. HT is equal to, that already we know. Transformer height plus clearance of 30 to 60 centimeter. Now similarly tank length LT, you can get this. Then tank width WT. Now losses will be given by 12.5 ST theta plus 8.70 AT theta. Now dissipating surface of the tank ST will be given by, we are neglecting top and bottom surfaces here, 2 HT, it is dissipating surface of tank 2 HT. LT plus WT is equal to 1.5, 1.1 plus 0.6, 5.1 meters. Now from this equation, whatever the total loss is there, it is 7 kilowatt, 7000 watt we can say, and this is 12.5 is given, 12.5, then 5.1 into 35 theta 8.78 AT theta is 35. Now from this we can get the area of all the tubes AT. Now dissipating area of each tube AT is equal to pi diameter of the tube given, average height or length of the tube, average height or length of the tube, this is your dissipating area of the tube. Now put these values, you will get number of tubes. Now going further, the arrangement in this case, yes, if the tubes are placed at 7.5 centimeter apart between the two tubes, there is a 7.5 is the distance. Then the number of tubes that can be provided along 110 centimeter and 60 centimeter sides are. So these are the given 110 divided by 7.5, 60 by 7.5. These are 15 and 8. Therefore, number of tubes that can be provided in one row all around is 2 into 15 plus 8. This is 46. But since there are 74 tubes are to be arranged in second row also. If 46 more tubes are provided, 46 plus 46 in second row, then total number of tubes provided will be 90. So it's much more than 74. What? With the 13 and 6 tubes, if we try for this 13 and 6 tubes along 100 centimeter and 60 centimeter sides, total number of tubes provided will be 2 into 13 plus 6, it is 76. Though 74 are only required. Now, by taking this into consideration, we can place the tubes in this fashion. This is about the numerical. Now we'll discuss the next point, that is voltage regulation of a transformer. So already we know what is voltage regulation of a transformer. It is defined as the change in secondary terminal voltage V2 from no load to full load at constant primary voltage and temperature. It is expressed as mathematically E2 minus V2 divided by E2 into 100. So whatever the E2 is there, it is no load, V2 is full load divided by no load. So normally the secondary terminal voltage of transformer when no load is connected to the transformer is known as no load voltage. At no load, the secondary terminal voltage will be equal to induced EMF in the secondary winding. It is E2. Full load voltage, it is the secondary terminal voltage of transformer and rated load is connected to the transformer. We will denote it by V2. We will denote it by V2. So voltage regulation of a transformer formula. The approximate expression for voltage drop E2 minus V2 in a transformer as referred to secondary is given by. So just considering secondary, we can take this formula and substituting here in this case. This is the percentage voltage regulation. So in the percentage voltage regulation, what we need to remember is, so whatever the voltage regulation is there, it should not increase. It should not increase. It should be within some limits. So if I say your no load terminal voltage is, let us say, 220 volt and load terminal voltage is 200. Again 220 minus 200 divided by 220. Again, if this particular, whatever the voltage regulation of this particular quantity is increases, it means what? There is a big change in the no load voltage to the full load voltage. So whatever transformer we are designing, it should not have that much change. It should be somewhat same. So we need to design a transformer in such a way that whatever the voltage regulation of a transformer is there, so it should be small. So here the positive sign is used for a lagging power factor and negative sign is for leading power factor. It is clear from the above expression that the voltage regulation of transformer does not depend only on the magnitude of load current, but it also depends on the type of the load. So the transformer regulation is positive for the resistive and inductive loads but it can be negative for the capacitive loads. This is about the voltage regulation of a transformer. So in the next, we'll solve some examples on all the design aspects of the transformer. Thank you.